things are starting to get interesting. In the first video, we set up a space-time diagram for my frame of reference and started to plot things paths in that space-time diagram. And then we thought about our friend Sally, who right at time equals 0 is at x equals 0, but she's passing me up at a relative velocity of half the speed of light in the positive x direction. So after 1 second, she has gone 1.5 times 10 to the 8th meters in the positive x direction. After 2 seconds, she's gone 3 times 10 to the 8th. And then we assume that she was part of a train of spaceships. So 3 times 10 to the 8th meters in front of her was another spaceship. And it's moving with the same relative velocity relative to me, or in my frame of reference. So at time equals 0, it's 3 times 10 to the 8th meters in front of me. But then at time equals 1, if we take this point in space-time, in my frame of reference, that ship is now has, so t, let me write this. If we look at my space-time coordinates, t is equal to 1 second, and x is equal to 4.5 times 10 to the 8th meters. That's if you look at my space-time coordinates. But what about Sally's space-time coordinates? Well, to figure out Sally's space-time coordinates, we go parallel to the x prime axis and see where we intersect the t prime axis. But that's still t is equal to 1 second. This is t is equal to 2 seconds. This is t is equal to 3 seconds. So t, or I should say t prime is equal to 1 second. T prime is 2 seconds. T prime is 3 seconds. So t prime is equal to 1 second still. And so in general, we can say that t prime is going to be equal to t. But what is x prime going to be equal to? So x prime, well, to figure out x prime, you go horizontal to the t prime axis and see where you intersect the x prime axis. And you see that it's 3 times 10 to the 8th. 3 times 10 to the 8th meters. And hopefully this makes intuitive sense. If it doesn't, pause the video and really think about it. Because in her frame of reference, that spaceship looks stationary because it's moving with the exact same relative velocity to me. It's going to continue to stay 3 times 10 to the 8th meters in front of her, which is exactly what we see. So that's why its x prime coordinates stay 3 times 10 to the 8th meters. From my point of view, it's getting further and further away from me at the relative velocity at 1.5 times 10 to the 8th meters per second. So how do we translate between our x coordinates? Let me do this in a different color. Between our x coordinates and our x prime coordinates. Well, you see for these examples where we see x prime is going to be less than x. And that should also make sense because especially for this case, it's stationary from the s prime point of view, but its x is continuously increasing as time passes on from my frame of reference, from Sal's frame of reference, from the s frame of reference. So if we start with x, we should subtract something. And the difference between the two, the discrepancy between the two, is going to be the relative velocity times time. And so for this particular example, we saw that 3 times 10 to the 8th meters was equal to 4.5 times 10 to the 8th minus the relative velocity 1.5 times 10 to the 8th meters per second times time, which was 1 second. And I didn't write the units, but if you write the units, it all works out, and you get exactly this. So hopefully that's starting to get you comfortable with having these two coordinate planes or two space-time diagrams on top of each other. And the reason why the blue one is distorted is because it's on top of, they're moving with a relative velocity relative to what I'm considering to be a stationary frame of reference, which is mine. Obviously, there's no such thing as an absolute stationary frame of reference, and we'll talk more about that in the future. But what I now want to focus on is that photon that I emitted at time equal 0. Because we saw it moves with the speed of light in my frame of reference. After 1 second, it has moved, its x coordinate is 3 times 10 to the 8th meters. After 2 seconds, the photon is at 6 times 10 to the 8th meters. But let's see what that photon looks like from the s prime frame of reference, from Sally's frame of reference. Well, from Sally's frame of reference, let's think about that photon after 2 seconds. So the photon's right over there. So t prime is equal to 2 seconds. 2 seconds. But what is x prime? What is x prime going to be equal to? Well, x prime, we go parallel to the t prime axis, is 3 times 10 to the 8th meters. 3 times 10 to the 8th meters. So in her frame of reference, it took that photon of light 2 seconds to go 3 times 10 to the 8th meters. Or it looks like the velocity of that photon is 1.5 times 10 to the 8th meters per second in the positive x direction. And this should hopefully make sense from a Newtonian point of view, or a Galilean point of view. These are called Galilean transformations. Because if I'm in a car and there's another car, and you see this on the highway all the time. If I'm in a car going 60 miles per hour, there's another car going 65 miles per hour. From my point of view, it looks like it's only moving forward at 5 miles per hour. So that photon will look slower to Sally. Similarly, if we assume this Newtonian, this Galilean world, if she had a flashlight, right over here, and right at time equals 0, she turned it on, and that first photon, we were to plot it on her frame of reference. Well, it's going to go the speed. It should be good. It should go the speed of light in her frame of reference. So it starts here at the origin, and then after 1 second in the s prime coordinates, it should have gone 3 times 10 to the 8th meters. After 2 seconds, it should have gone 6 times 10 to the 8th meters. And so its path on her space-time diagram should look like that. That's her photon, that first photon that was emitted from that. So you might be noticing something interesting. That photon, from my point of view, is going faster than the speed of light. After 1 second, its x-coordinate is 4.5 times 10 to the 8th meters. It's going 4.5 times 10 to the 8th meters per second. It's going faster than the speed of light. It's going faster than my photon. And that might make intuitive sense, except it's not what we actually observe in nature. And anytime we try to make a prediction, it's not what's observed in nature. It means that our understanding of the universe is not complete. Because it turns out that regardless of which inertial reference frame we are in, the speed of light, regardless of the speed or the relative velocity of the source of that light, is always going 3 times 10 to the 8th meters per second. So we know from observations of the universe that Sally, when she looked at my photon, she wouldn't see it going half the speed of light. She would see it going 3 times 10 to the 8th meters per second. And we know from observations of the universe that Sally's photon, I would not observe it as moving at 4.5 times 10 to the 8th meters per second, that it would actually still be moving at 3 times 10 to the 8th meters per second. So something has got to give. This is breaking down our classical, our Newtonian, our Galilean views of the world. It's very exciting. We need to think of some other way to conceptualize things, some other way to visualize these space-time diagrams for the different frames of reference.